Swayam Prabha. Digital India. Educated India.
This maritime engineering, as you see, is a very special program which has got multidisciplinary input from mechanical, civil, structural, aerospace, naval architecture, chemical engineering, electrical, electronics, applied mechanics. It's a multidisciplinary program. You will find this program is completely different, dedicated to industrial training and thorough capacity building on the new trade of maritime sector. It's a grooming economy which will give you a lot of job opportunities and research frontiers as far as India is growing. And the Blue Corridor effect, which is planned by Government of India, is one of the important mission which requires maritime engineering growth to happen in the country. So this program caters to expected that capacity building in this program.
Friends, this is part of a material science engineering laboratory which becomes one of the teaching aid for the maritime engineering program. So when you talk about materials innovation in maritime industry, though concrete and steel have been conventional candidates of choice for engineers, for example, we have titanium vessels, high-speed craft boats made of fiberglass. These are all advanced materials which actually do not come across conventional standard design code of practices. We conduct box furnace test, tube furnace test, vacuum arc melting, induction melting, vacuum induction melting, vacuum sealing unit, which are all present in this laboratory is a small segment of material science laboratory. Friends, a typical furnace where the operating temperature for testing specimen can go as high as 12 degrees Celsius. Generally at room temperatures and ambient condition, the mechanical properties will not alter much. As you see in the course lectures, you will notice that strength of the material get degraded when the temperature rises beyond 600. Therefore, when you talk about fire resistant design, you must also choose an alloying element such a manner that the strength doesn't degrade beyond 600 degrees Celsius at all. Welcome to the ambience of IIT Gandhinagar lecture theatre. This is one of the interesting classrooms where the maritime engineering classes will be conducted. We have got state-of-the-art projection facility and good audio-visual recording systems. Once the lecture is over, you see the system here. We can generate the PDF files of the lecture directly and you can email the PDF files directly to your email IDs. So it's a state-of-the-art facility we have in IIT Gandhinagar where the lectures are lifetime recorded and shared with the students immediately. This is the IIT Gandhinagar library. This has got all collections of books which are referred as the standard textbooks and references for the course and the program. It also has lot of online editions of design code of practices and reference materials and e-collections of various video lectures of international courses and programs related to maritime engineering. We will be taking you around to the advanced material manufacturing units. So you will have state-of-the-art facilities available at IIT Gandhinagar. So welcome to the program to join MTech and PhD at IIT Gandhinagar Maritime Engineering. So please try to enjoy and take the advantage of this to the maximum. Welcome to the program and welcome to IIT Gandhinagar. Friends, welcome to the lecture on Maritime Structures Under Fire, Blast and Explosion, a course offered by Department of Maritime Engineering at IIT Gandhinagar. We have been learning about understanding the characteristics of explosion because this is one of the important design input for an engineer to understand how the explosion proof equipments and how explosion consequences on structures can be reduced. We have been discussing fire earlier. Now we are talking about blast and explosion together. So in this sequel lecture, which is lecture number 13, we are going to discuss more about explosion. Let us see, in the last lecture, we learnt about the effect of fire which exists till there is energy available, and fire can also cause explosion which can be classified as pool fire, jet fire, flash fire, etc., which are also dangerous scenarios in industrial structures. Design parameters to compute different categories of fire based on burning was discussed. We also understood that TNT is a referral material being used to refer to explosives in industry. Therefore, any explosion happens is always computed or assessed in terms of TNT equivalence. This will help us to compute damage caused by pressure waves, because damage caused by pressure waves of TNT already established in literature. So, any new explosive should be referred to as a TNT equivalence, so that this can be understood as the effect of the damage. Furthermore, we understood that BLEVE is one of the most disastrous and serious consequence of explosion which can happen in industrial structures. PCE, PVE and BLEVE have serious consequences if they occur. So, we cannot control the causes because they are accidental, but we can mitigate or reduce the effect of those, what we call consequences, to reduce the risk on the given structural system. So, in this lecture we will further learn more about the explosion characteristics as we go forward. The explosion can be classified as 4 basic types, which we saw already: vapor cloud explosion, pressure vessel explosion, boiling liquid expanding vapor explosion, which is more disastrous, condensed phase explosion and dust explosion. So, now we will see an example of understanding the damage computed by this. Let us take an example on the screen. A vessel contains propane to its full capacity, and it is assumed that a BLEVE is going to occur at 90% of its critical temperature. Okay? We are assuming this as a worst scenario. The initial pressure based on the saturation pressure of the critical temperature is about 2104 kilopascal. For the saturated liquid, internal energy, entropy and specific volume are available in handbook. You can also compute them from experiments. So, chemical engineering handbook will be able to give you these properties for any flammable mixture. In this case, it is propane. Now, we all know that propane expands into natural environment, setting a dead state property as about 1 bar, which is at 25 degrees Celsius. What is asked is, calculate the energy release occurred during BLEVE. Use the following data. The critical temperature of propane given from the handbook is 369.8 Kelvin. Internal energy at critical temperature and dead state is available in the handbook. Internal energy is this, and at the dead state is this. This is at the critical temperature, it is at dead state. Specific volume at critical temperature and dead state is given by this. Entropy at critical temperature and dead state is given by this. These are all taken from chemical engineering handbook. Friend, one can also conduct experiments to compute these values. Let us try to now find out the energy imposed by BLEVE. Remember, in this case BLEVE was assumed. Okay? So, we already saw this equation, we remember in the last lecture, in the sequel of explosion. Energy released by BLEVE can be computed based on this expression, where U refers to internal energy, V refers to the specific volume and S refers to enthalpy. So, we have said that critical temperature and dead state, the values are substituted here. Pressure is given as atmospheric and the volume at critical temperature and dead state are substituted from here. Then T naught is taken as 298 and the entropy is substituted from here, and we now compute the energy released by BLEVE is so many kilojoules per kg. Friends, this is a maximum energy released by propane system under BLEVE. Lesser values are possible, with lesser values of superheat. Okay, we have taken the maximum possible value. Having computed this, we try to find out from the temperature, from the handbook for propane, what is the normal boiling point, critical temperature and critical pressure, which we needed actually in this calculation. Okay, in this calculation. So, we can also have many other components available in the table, which are called thermodynamic properties of selected chemicals. The detailed table is available in chemical engineering handbook. You can find out from them and you can refer them for your calculations further. Let us do another example where a cylindrical vessel of 50 cubic meter contains liquid propane and it is stocked at room temperature. Because of contact of extensive heat and fire engulfment, this can result in a BLEVE, which can also result in loss of containment through a safety valve. At the time of explosion, the temperature is said to be 50 degrees Celsius. Estimate the scaled overpressure at a distance of 125 meters. Friends, remember, I have a vessel, it explodes. I am trying to find out the effect of this at a distance of 125 meter, and the effect is always measured in terms of overpressure, what we called as scaled overpressure. Let us try to find out that. Filling degree is taken as 25, which is given. It is always expressed as percentage. Temperature is 50 degrees Celsius, so we convert to Kelvin. The mechanical energy released per cubic meter of the vessel, which is a function of explosion temperature and filling degree, is given by this equation. So, the literature reference is given here, equation I am giving you for your reference. The mechanical energy released from a pressurized vessel is given by this equation. It is an empirical equation. Therefore, some of the constants which you use here are need to be carried as it is. So, we substitute the values whatever we computed from here, and for temperature we compute in Kelvin and so on. So, we compute the energy release is about so many megajoules per cubic meter. The total energy released is, this is per cubic meter. I have 50 cubic meter of content, therefore, I can find the total energy release, capital E, is into 50. So many megajoules. Now, as I said in the beginning, the impact caused by this BLEVE should be always measured in terms of TNT equivalence. Let us see how to compute the equivalent mass of TNT for this explosion. So, this is given by this relationship, mass of TNT equivalence is given by this relationship, where eta in this is the efficiency of explosion. Usually it is taken as 1 to 15%. Friends, remember, in case of any explosion, the completeness of explosion is never 100%, it is always less than 20%. Okay. So, usually the efficiency of explosion is usually designed as only 1 to 15%. So, any number can be taken here as eta. E, of course, the total energy released, which we know here, and E TNT is the energy of TNT, which is given in the literature. So, I substitute them here, 15%, so many megajoule, this is kilojoule, therefore 10 power 3, and is substituted here. So, now what I do, for the energy released by this accident, which is given in a chemical containing in this cylindrical vessel, without even knowing what was the chemical, though it is liquid propane, I do not want to compute the damage based upon every chemical. I always convert this into equivalent TNT, and he did that. So many kg of TNT is equivalent to this energy released by propane. So, I can now compute what is called scaled distance. This is given by this equation. So, scaled distance is given by this equation where r is the point of our interest. So, I want to compute what is the effect of this at 125 meters and cube root of this. We already have this value computed. So, the scaled distance now comes to be about 69 meters. Then once I have the scaled distance, I can compute the overpressure. Let us see how. Use this equation or use this curve. If we know the scale distance in meter per kg, ZE, I can always compute the scaled overpressure from this. For example, in this specific case, if we know this value is 68.87, I will come and plot 68.87 somewhere here, let us say 10 and 100, let us say 68 is somewhere here. I try to find out this value, and that will be my scaled overpressure PS. Okay. So, I can compute the scaled overpressure, found to be 0.04 bar, because this is 0.01, this is 0.1. So, it is between this. Okay. So, 4 kilopascal. This is all in bar. Okay. So, 4 kilopascal 0.04 from the plot. Friends, you can also draw this plot from the MATLAB program shown here. So, you can type this coding lines on MATLAB, you will be able to get this plot back again, and from this plot you can always find out for a known scale distance what is actually the peak overpressure, scaled overpressure, because this is called scaled distance. Okay. So, I can compute this. So, this is how the scale distance can be computed. In case of offshore platforms, a BLEVE is likely to occur when exposed to fire. The possibility of BLEVE can be assessed using Reid's massive nucleation theory given by Reid in 1979. The zone of spontaneous nucleation of vulnerable petrochemical is explained using this figure. Let us look at the pressure temperature diagram of vulnerable petrochemical or hydrocarbon. As seen in the figure, the tangent line drawn from the critical point to a point where the ordinate represents atmospheric pressure is the tangent line. Okay. Horizontal line, the horizontal line is drawn from a typical pressure value to intersect this curve. A typical pressure value to intersect this curve. So, let us say from a typical pressure value, I draw an horizontal line to intersect this curve. From the point of intersection, a vertical extension is shown. Okay, vertical extension is shown, is extended. Now, this will now govern the enclosed area. This enclosed area indicates the spontaneous nucleation of the petrochemical chosen. This is the suitable scenario for BLEVE to occur. So, this curve will help us to know what is the scenario at which BLEVE can occur for a given condition. So, if you know the operational temperature and pressure, you can always get the boundary of this curve drawn from here, and this will give me at what temperature range and what pressure range, okay, BLEVE can occur. So, this can be a very handy calculation in industrial sectors where this can be even programmed, and depending upon the emission of the flammable materials at its temperature known and pressure known, one can compute the possibility of BLEVE. If BLEVE is likely to occur, then one can start activating the mitigation effects so that the consequences of BLEVE can be reduced. Okay, that is the idea here. If you look at BLEVE, the effects of BLEVE are of three types. One is thermal radiation, other one is overpressure effect, which is called because of shock waves, and projections of fragments of the pieces. The thermal radiation is also accounted for fireball. The flow of radiation per unit emissive surface area is given by the following equation. It is an empirical equation whose values are fixed based upon the experiments conducted. In this equation, which gives me the flow of radiation per unit emissive area, Fr is the ratio between energy emitted by radiation and total energy released by the combustion. Usually it is about 25 to 40%. It is a ratio. Delta H combination is the heat of combustion of the material expressed in kilojoules per kg. P naught is the initial pressure at which the flammable chemical is stored in megapascal, and PV is the vapor pressure of the chemical. So, one can use any of these three equations depending upon what data is available to us to compute them. The radiation received from a distance x from an emitting point is computed using something called geometric view factor and fraction of energy transfer tau, which is given by these equations. This is also called as atmospheric transmissivity. In this equation, Pw is called partial pressure of water at ambient temperature. This equation is suggested by Roberts in 1952, later revised as 1982. One can also find out alternatively the radiation effect using this equation. So, friends, intensive radiation depending upon the mass of the fuel can be also computed from here. So, BLEVE also causes overpressure effects, which are generally difficult to predict because the duration of depressurization is a complex quantity. In the last lecture we saw that once overpressure occurs, it gets into negative before it comes to atmospheric, and it is very difficult to compute how long this will stay in suction. Okay? You can compute the time arrival, you can compute this time, but this is difficult to compute. So, therefore, BLEVE also causes overpressure effects, which is generally difficult to predict because the duration of rupture depressurization is a complex quantity. Having said this, let us now expand our discussion to condensed phase explosion. Condensed phase explosion occurs when the explosive material, may be liquid or solid phase, is the candidate. Such explosions are very common in organic based hydrocarbons. Examples could be RDX and DNT. Look at the following reaction. You have an organic compound added to N3, you get the nitrogen gas released. Okay? These are very common in organic based hydrocarbons. This is called condensed phase explosion. Addition of fulminate radical, for example, mercury fulminate, lead fulminate, etc., should also cause decomposition to form ready explosive. Sometimes people also have this kind of combinations, which is seen in the chemical process as also becoming or converting to an explosive. Even under slight impact of friction, the lead fulminate can result in an explosive. These are termed as percussion crackers. Acetylide radicals in presence of even heat and sunlight and slight impact can also decompose to form explosion. So, explosions are not actually what you stock on any industry. Explosion can be an outcome of any internal reaction also of any combustion or manufacturing chemical materials. A small radicals added in terms of acetylite or even lead fulminate, mercury etc. can also cause them to become a explosive. So, explosives are not actually manufactured, no? The chemical process convert them to explosives. Having said this, there are also inorganic based condensed explosives like lead stiphanate. Therefore, friends, explosive is a substance we can originate either from organic or inorganic compounds. Okay? Even a chemical manufacturing industry can also land up in explosion accidents, not necessarily hydrocarbon industry. Condensed phase systems like solid and liquid have high heat of decomposition and therefore, they cause or they result in detonations. Detonation is one form of explosion where solid or liquid vapors are involved. These are very common material which are routinely used in chemical process industries. The examples could be organic peroxides, acetylenic compounds and nitration mixtures. These are all very common in fertilizer industry, paint industry, food grain production industries etc. These are all very common. Okay. They can also form explosives. Furthermore, friends, as we saw and understood, the blast and fragment effects caused by explosion are very severe. The energy released by them in terms of equivalent mass of TNT can cause severe damage which need to be understood. The last of its kind in explosion, what we also fear of is dust explosion. We can also define dust as a particle whose diameter is less than 50 mu. A dust explosion is a rapid combustion of fine particles suspended in air within an enclosed location. So, if you have a contained area which has got very fine particles, can also explode. They can occur under presence of dispersed powder which is a combustible material in high concentration of air. Therefore, in dust explosion, the main factor which contributes to this is fuel air explosion. Dust particles emitted from paper mills also produce serious dust explosion hazards. One of the simplest method to control dust explosion is to maintain relatively high level of humidity. That is why you see in many of the industrial plants like paper industry, sugarcane industry etc., they will keep on pouring water. So, that relative humidity of high level can prevent dust particles to get afloat in air and dust explosions can be avoided. If you have very small fine particles in dust, it generates high surface area to volume ratio. These fine suspended particles can explode in a fashion similar to flammable chemicals or gases. In case dust is suspended in air, even a small concentration of flammable gas can contribute to severe explosion. The dust particles can also join the flammable mixture to cause explosion, which can have more catastrophic effects. Dust explosions are frequent hazards in coal mines, grain elevators and other industrial structures, not necessarily maritime industry, because sometimes port and harbors can also stock food grains. There are coal jetties which stock coal in large amount. They are very fine dust particles, and when they mix with flammable chemical, even a small concentration of flammable gas, this can cause a very severe explosion which need to be also taken care of in the design aspect. Many common materials burn to generate dust, like coal, sawdust. Nowadays the modern manufacturing of furnitures which creates sawdust can also cause explosion. In addition, powdered metals which are used for powder coating, what they call for different structural systems like aluminum, magnesium, titanium, can also form explosives when they are suspended in air as a fine divided particles. Dust explosion therefore friends can cause a major damage to structures, equipment and human, because they can also result in overpressure or shock waves. In a confined space, sudden depletion of oxygen can also cause something called asphyxiation. In case of coal mines, incomplete combustion of dust may produce large amount of carbon monoxide, causing deaths. So, explosive dust arises during transporting grains, coal mining and flour mills. One of the classical example of dust explosion is which one occurred in Washburn Mill area in Minneapolis in USA in 1878, killing 18 workers apart from damaging many buildings located adjacent. So, dust cannot be considered as a ignorable factor even in flour mills, sawdust mills, coal bunkers, grain transportations can have probability of explosions. So, friends, explosions are important source of accidental loads. Irrespective of type of structure, all structures suffer potential threats from these explosion loads. Therefore, understanding the process will help the designer implement various design practices that effectively address the consequence of explosion. So, friends, let us come to the summary of this lecture. In the sequel of explosions, this is the last lecture we had to understand more about explosions. We understood that a sudden release of gas or a flammable chemical mixture can cause fire, can also result in explosion. Explosives are generally compared with TNT. Therefore, we try to compute something called TNT equivalence to understand the damage caused by explosions. Explosion need not be only with hydrocarbon industry which is related to maritime industry, can be also even occurring from food grains, transport, sawdust, coal mines, etc. These are called as dust explosions. They are as severe as Blevy because they can also produce shock waves which can cause peak overpressure. We already saw the effect of peak overpressure on human in terms of lung damage, ear damage, etc. Therefore, even dust cannot be ignored, and all industries, we can say all manufacturing units are suffering from potential threat from explosions. Explosives are not separate chemicals. Even conventional manufacturing units which involve chemical reactions can also turn to be explosives. It all depends upon the operational temperature, ambient conditions and pressure, and the quantity of discharge and the source of heat. So, all these are inevitable. Therefore, friends, explosion accidents is very difficult to avoid. What we can do is we can reduce the consequence of them if we know the process and if we can able to find out this. And we also learned how to compute the scaled distance and the effect of overpressure, scaled overpressure we say. scaled overpressure. Once we have the scaled overpressure computed, we already know from the table how to compute the damage. The damage is in two ways, mostly it is qualitative, sometimes it is quantified also. Okay. So friends, I hope you understood this lecture and realized the importance of learning more detail about explosion processes, which is not completely different from fire. They are actually contemporary and they convert one form to another. Therefore, fire and explosion are, let us say, two faces of a coin. So, either way, this way the coin can be swapped. So, as maritime industry involves stocking of flammable materials in offshore for processing and production, even onshore in port and harbour for stocking LNG, CNG, stockyards, etc. Even industries where post processing takes place of the chemical, or even bottling plants of LNG, CNGs, we have potential threats of explosions happen. Therefore, one need to understand thoroughly this process as we explained in the sequel of the lectures. Hope you have followed them. Please also refer to the reference materials suggested by us in the SwayamPrabha website. Should you have any questions or any queries, you are most welcome to write email to us, and instructors will be able to give you responses positively to satisfy your answers, as well as more explanations will be shared. Thank you very much. Namaste.